Welcome to a video here on the channel, and yeah, the world, as I'm sure you're well aware, is in a little bit of a pickle, I guess you'd say. But what we're going to do here is take a different perspective as to everything you'll see on the news about this new virus and everything. Social media, it's not a good place, so I thought I'd bring it back to the basics of data analysis. Now, what I'll be looking at here is the pure mathematics on the situation. And obviously in the real world, the mathematics tells you trends, but obviously it can't tell you what's going to happen, how people are going to react, how governments are going to influence these trends. So let's get into it. All right, so usually the way these kind of viruses and general disease outbreaks work are modeled by a logistic curve. And you can see this logistic curve all over nature in biology, demography, and epidemic modeling. Now, the way it works in demography, for example, the study of population, is that at the start, when everyone is on low incomes, you generally get higher birth rates, causing the exponential growth in exponential growth in the population. Now, when you get roughly halfway, that's what the model tells you, you find that it turns from an exponential curve into a logarithmic curve. And again, in demography, the reason this kind of thing happens is because people get richer, they start to have less children. And so similar things happen when a virus outbreaks, such as is happening at the moment. And so mathematically, the way you could look at this thing is that the first derivative is always positive across the whole time. But in the first half, the second derivative is positive, i.e. it's increasing at an increasing rate, and it's negative after halfway, and so it's increasing but at a decreasing rate. So let's move on. And so first we're going to look at how it all worked in China. Now, the news doesn't particularly make this obvious. Now, we can see a pretty clear logistic curve in the data that shows from China from the 22nd of January all the way to mid-March. And you can see that I've drawn a curve over there which shows you sort of a generalized model and how the curve of the number of cases in China works around that. And as you can see, it fits the logistic curve pretty well. It's exponential roughly until about February the 12th, February the 11th. And then it becomes logarithmic after China put in the lockdown and in Hubei or Wuhan, that sort of place. And that's what you find. The growth rate starts to slow. And in a particular population size, or whatever that may be, what you'll find, the reason if the entire population becomes has the disease, which is very unlikely in most cases, the logistic curve works because if 10 people are in a room and 8 of which have it, and you're all walking around bumping into each other, the more times you'll be bumping into people who already have the virus. And so the more you grow, the slower the growth rate in the growth will be. I'm sure it makes sense. And so this is the graph of Italy from the 15th of February to the 12th of March. As we can see, it's in the exponential section. Now, you may be asking, well, where's halfway? And the answer is we don't really know. That's the big question. And you could look at the situation that's going on in Italy with the lockdowns and assume that it's not too far away, but you can't really say. And the only really mathematical analysis we can do on this at the moment, not taking into account government intervention, is separating the exponential and the logarithmic sections of the logistic curve. And so here is the second half of China, which obviously looks like the logarithmic section of the curve. Now, let's get into some regression analysis of the data which we have. Now, there are many ways we could look at this problem. We could find a model which fits the data we currently have and get it to fit as best as possible. I have a high R² value, but this is not always the best thing to do. Now, it does seem strange for a virus to break out as a trend of t to the power of 4 instead of exponential value of t. Because like I said before, things in nature generally work exponentially and not really to the power of 4. That's not generally how things work. So if we do do a regression of t to the power of 4, then we can see the data in the next slide. Now, just to specify a few things in the model, C of t is the number of cases at time t, and t, the value, is the vector of time from 1, 2 to t over 2, where we expect the growth rate to slow up to t. And so the models we're doing is up to somewhere up to t over 2, wherever that may be. And so yeah, this is the best fit model, which I said about for ct hat is equal to beta 0 hat plus beta 1 hat times t to the power of 4. So as you can see, we have a pretty high R squared of 0.9989. Now, the graph of ct against c to the power of 4 looks pretty linear. And so obviously you'd expect a high R squared from this. And from the data output we have, from the regression output we have at the bottom right, we can see that the t to the power of 4 is statistically significant and the model is overall significant. But what I found with this model is that it doesn't predict the future particularly well, even in the period t plus 1, i.e. tomorrow. What I found is that over time it gradually becomes too far off what I expect it to be. And this is, I guess, what I would expect, considering it's not the model that we would assume takes place in nature. So let's have a look at an alternative. Now, this is a strange transformation on the data which I applied, taking the natural logarithm of c of t and taking the cubed root of t as well. Now, another way of doing this transformation, which I would say is probably better, is also taking the log of t. So the model would become, I'll write it down for you here, so it would be the natural logarithm estimated of c of t is equal to a0 hat plus a1 hat times the natural logarithm of the value of t. And this would give us pretty similar results as the models between logarithm and square roots, cubed roots sort of look similar. And so yeah, as we can see, similar situation here, pretty linear graph, statistically significant, independent variables. And let's look at the exponential model at which we would expect the data to fit. Now, as you can see on the graph, it does look less linear in our of graphing the natural log of ct and against t. And so yeah, at the bottom here we can see the piecewise function of what we would expect c of t to follow, which would be the exponential value, or the exponential of t from t to 0 to t over 2, i.e. halfway, and then we would expect to take a logarithmic value of t from t over 2 to t. And as you can see in the regression output, same situation, reasonably high R squared, not that we're too worried about that, and statistically significant t values. But the way the data looks at the moment is that, similar to the last model, it looks still kind of logarithmic. So the reason I would apply a natural logarithm to t, it would give a more linear graph. However, it's not quite as accurate still when I try and estimate this in the real world. And so now we have the data, let's look at the forecast. And the way obviously we do this from our various regression models is to just extrapolate with higher values of t. And so t, for example, starts from 1, 2, 3, as I said before. And so say, for example, if today we're in t equals 20, if we want to find out what this could be in 10 days, i.e. t equals 30, then we use one of the models that we've used today, plug in the value of t for 30, and then estimate what we would have as the log of c of t at time equals 30. And then to get the actual value of the number of cases at time t, or t is 30, then we just apply the exponential function to the logarithmic function of c of t to get c of t, as you see there. And so generally what I have found from doing these forecasting, now that they're not particularly rigorous forecasting models, but they generally follow the trend And yeah, what I have found from applying these is that these models can be they can get close. Obviously, it's not going to be perfect to what the value will be tomorrow, but if you use the highest value and the lowest value, it can give you a decent bound as to what the model is going to be in the next few days. And obviously this bound will grow larger, the deviation of these will grow larger over time, but I found them generally to be a reasonable boundary of how the number of cases moves over time. Now I just want to specify that these 3 models here are for Italy, so the numbers apply to how many cases there are in Italy over the course of time. And yeah, so the way I've said before, is that we can look at the best fit models and we get a reasonably high R-squared. And yeah, I've stressed that you shouldn't apply too much to R-squared, as the models I found, as the ones which follow a trend at the moment, aren't necessarily the ones that will keep on happening over time. And as you expect with nature, things converge to an exponential trend up to halfway point, and then they'll tend to a logarithmic trend for the second half of the period. And yeah, so the way we can look at this in the real world is that over time, over maybe the next few weeks, possibly months, I don't know how long this will go on for, but yeah, you will, if you can notice when the halfway point is, when it turns from the exponential to a logarithmic trend, then you can sort of see from the data that things are managing to slow down. You could see in the data from China when things were starting to slow down about halfway in the data. So hopefully the indications will be pretty similar in European countries, but we'll have to see. And so yeah, the data I got, I'll leave a link in the description. It's a very good data source showing you all the new cases, current cases, active cases, recovered deaths from this thing all over time. It's a very good source, so yeah, I'd go and check that out. But yeah, as I said before, the big question about how to predict and forecast how many people this is going to infect, how many people this is going to kill, is pretty much based on when halfway is in this model. And that's a very hard thing to predict, and largely depends on how governments and people in general work together to isolate themselves and yeah, take any measures they can to stay safe. So I hope you guys enjoy this video and take something from it. If you have any questions for me regarding anything I've said about this video, just drop me a comment down in the comment section below and I'll be sure to get back to you. So thanks a lot for watching and see you guys next time. Goodbye.